Hello AP Chemistry and welcome to the last two sections, so molarity and titration. Again, this is the basic introduction and it's sort of, it does tie in with what we talked about last year and it's about the same level to which we talked about it last year. We will talk about titrations more thoughtfully again later on in the school year. So first of all, molarity, right? Note that anytime we say concentration during the course of the year, we always mean molarity, right? That's what that's always going to be a stand-in for, right? There are other ways to measure concentration, right? Like grams per milliliter, right, is one way to talk about it, and we will talk about that sometimes, right? I guess more specifically, it'd be grams per 100 mils is one of the ways that we express concentration. There's also molality, which if we have time, we'll talk about a little bit later. But this is what we most often mean, right? And don't forget that this is moles of solute, right? Very important, right? Per, right? Liters of solution, right? So when we say that we made 100 milliliters of something, right, that gets to be our volume of solution, okay? And that's the moles of solute, and that when we're talking about an aqueous solution of something, right, now we are talking about solute plus water, right, which means that the mass, right, is no longer applicable, yes, as in like there is not a mass of the solution, right, there's a mass of solute that is dissolved in a certain amount of water, yes? Be mindful about that. All right. Your book goes through two different methods here, right? So this is making a solution from a solid. Make sure you can explain these, right? These are very simple free response questions that you might see, right? Wherein we would first need to figure out what mass of substance we need, and then we would get that. And then, depending on how many significant figures we need, right, we could use a volumetric flask. So a volumetric flask is a very, very specific piece of measuring equipment, right, that literally has one volume on it, right? So this entire flask measures one volume. That's it. That's all it does, right? So they are rather expensive, right? And that volume that it measures is typically known out to 2 or 3 decimal places, right? Which means that if we're talking about 100.00 milliliters, right, we are talking about 3, 4, 5 significant figures if we use a volumetric flask, right? No, right, or pay attention to the fact that that way outdoes, right, the significant figures that we can get from most of the massing equipment we would use, right? So whether or not you need a volumetric flask sort of depends on the level of accuracy that you need for your solution, okay? So make sure that you can think about that and reason through that, right? Because obviously if this mass is limited to 3 sig figs, the molarity of my final solution is limited to, ding, 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 3 sig figs, right? So the need for the volumetric flask, sort of varies. And then anyway, so we'd put in our solid, we would add water, right? And then we would add water only to about like here, right? And then we would swirl, swirl, swirl till it dissolved, right? Like it says here, swirl to dissolve. And then we would top it off to that last volume, okay? Here, this is the instructions for making a dilution, right? Do note that that's where that M1V1 equals M2V2 equation comes in, which is only ever applicable in the singular scenario where we are making a dilution, right? Because it does not take into account a mole ratio. So if you are prone to confusion, like we talked about last year, don't use that equation, right? Just use normal stoichiometry, right, and do some conversions, is what I might recommend. But anyway, we would calculate how much stock solution we need, and where our stock is the more concentrated version, right? So that's our stock, or our concentrated version, right? We would figure out how much of that we need, and we would add it to our volumetric flask, right? Then again, same thing, we would add water, swirl, and then top off to our final volume, okay? Again, depending on the level of significant figures that we need, because, that will vary. All right, now, titration, a couple of things to note here. Note that the output of titration, the output piece of information, is always moles of unknown, right? So every time we do a titration, whether it's an acid base or a redox or something else, right, it's always moles of unknown. That's what the output information is, okay? Because a titration always starts with, so here is our unknown, right? And because it's a liquid, right, we have a volume of it, okay? Or it's an aqueous solution, I guess, right? And here we have our known, which is something that we know the concentration of and something that we also can know the volume of, right? Because it's in a burette, and a burette actually measures volumes very specifically, and hopefully we'll get a chance to use those later in the school year. But anyway, we have our known, so we will know the concentration, we will know the volume, which means we can solve for moles of our known, which then we can use a mole ratio to then get to moles of unknown. And then what we do with that moles of unknown depends on what the goal is, right? We could take that moles of unknown and divide it by its initial volume to come up with molarity, right? Or if we had a solid unknown that we started with and we figured out moles of unknown, we could use grams of unknown divided by moles of unknown to come up with the, right, molar mass of that unknown. So it just depends on what the goal is, right? But the output information of a titration experiment is always your moles of unknown, yes? Based on the concentration and volume of your known, which gives you the moles of your known, which then via mole ratio will take you to moles of unknown. All right, now let's go ahead and talk about these practice problems because I just want to make sure we can translate them correctly. So what is the molarity or concentration of a sodium hydroxide solution if 48 mils neutralizes, which just is code for reacts, right, with 35 mils of that, right? So first off, it's a reaction, so we need a balanced chemical reaction to do this. So we have H2SO4 plus NaOH is going to give us Na2SO4 and water. All right, and then we know, so our unknown is the NaOH. So we are looking for the molarity of this, right? And we're starting from our H2SO4, right? So again, we have a volume, right? And we have a concentration. Okay, and then we will use our mole ratio, which says that for every 1 mole of, oh, this is H2SO4, sorry, I wrote the wrong thing. For every 2 moles of NaOH, right? So if we look at our steps here, right, and then the last step will be to take our moles of NaOH, and if I want to know the molarity, I've got to divide it by the initial volume, which would be 0.48 liters of NaOH. So then if we go through our steps here, right, so first we have this first step, which is just about coming up with the moles of our known, yes? That is the moles of known used to do the reaction, okay? Then next step is we would take our mole ratio, and that mole ratio allows us to convert that moles of known into moles of unknown, okay, being this. And then finally, right, we, in this case, used the volume of that unknown to come up with the molarity, right? Does that make sense? All right, which then brings us to the second problem, which says that we have a sample of iron ore is dissolved in acid. The iron is converted to iron 2+. The sample is then treated with this volume of this concentration permanganate solution, and the reaction occurs, right? And this asks us how many moles of permanganate were added, right? And so really that's just this step 1 that we did up here, right? And then step 2 is how many moles of Fe2. So now we're converting from the known to the unknown. And then step 3 is how many grams of iron were in the sample. So then if we were to write all that out, it's the exact same thing, right? So we would start with our 0.0472 liters of our MnO4 minus, right? And then we use our volume or concentration for every 1 liter. And then, so again, same first step. Now we're at moles of our unknown, moles of our known, so we've just solved for A. And then we will go ahead and take our 1 mole of permanganate, and that correlates with 5 moles of iron 2+. And then the question C asks us to convert to grams, so then for every 1 mole of Fe2+, we would say that's 55.85 grams of Fe, right? In that, to become a 2+ ion, all that happened to it was it lost 2 electrons, which is negligible in the land of mass, so we can just use the mass of iron, right? So then if we look at our steps again, it's the same thing that we talked about previously, right? Where, so again, this is step 1, which gets us to the moles of our known, right? This is our step 2, which converts to our unknown. And then we took that moles, and in this case, we wanted to figure out how much mass was in the sample, and we used molar mass last. Yes, does that make sense? All right. Thank you for listening. Be good, and I will see you soon.